put Stokes' theorem to work. And by that I mean, let's use it to compute an integral that will be very difficult to compute otherwise here. Let's take a look. Evaluate the circulation along C of f dot dr. For f is this vector field. Yikes, that looks a little bit messy here. For C is the line segment from 3, 0, 0 to 2, 0, sorry, 0, 2, 0, up to 0, 0, 1, and then back to 3, 0, 0. So if we wanted to do this, in a straightforward fashion, we'd have to parameterize each one of these three, calculate out three separate vector line integrals. We could do it, but it would be a lot of work here. Instead, what we're going to do is that we're going to use Stokes' theorem after we compute. So first we need to take the curl. So instead of computing this, we're going to compute the double integral of the curl over this surface S right here. Okay, well, let's get to work. The curl of f, okay, I hat, j hat, k hat, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z of sine of x squared, e to the y squared plus x squared, and z to the fourth plus 2x squared. Okay, so the curl will end up being I hat times the partial derivative with respect to y of this quantity here. There's no y's, that's 0. Minus the partial derivative with respect to z of this quantity right here. There's no z's. This is also 0. Plus j hat times the partial derivative with respect to z of sine of x squared. Well, there's no z's. We're getting an awful lot of zeros here. Minus the partial derivative with respect to x of this expression right here. And this will give us negative 4x. Okay, finally got a non-zero term here. Plus k hat times the partial derivative with respect to x of this expression right here. That will be 2x. Minus partial derivative with respect to y of sine of x squared. That's 0. And so our curl is just going to be 0, negative 4x, and 2x. Pretty simplified here. So now what do we have to do? We have the curl here. We have our normal vector. Okay, we need to find our normal vector. But really we should be thinking, okay, how are we going to go about doing this? Maybe the most thematic way to do this is to say, this is the graph of a function. This is a graph of a function, z is a function of x and y. How do we come up with this? Well, realize that this right here, this triangle, the triangle lies in the plane x over 3 plus y over 2 plus z is equal to 1. So, let's just assert this. This is clearly the equation of a plane here. And if we plug in x is equal to 3 and y and z are both 0, we get 3 over 3 is 1, plus 0 is 1. Plug in 0, 2, 0, 0 plus 1 plus 0 is 1. Plug in 0, 0, 1, 0, 0, 1 is equal to 1. Okay, so that shows that, yes, this is the equation of this plane here. And if we rearrange this, this would be z is equal to 1 minus x over 3 minus y over 2. So what's going to be our parameterization? Time to use this part of the chart. R of x, y is x, y, and f of x, y is this right here, 1 minus x over 3 minus y over 2. And we're going to need the normal vector here. And so this is going to be Rx cross R sub y. And I'm just going to write this down here. Is going to be, let's see here, the negative of the x partial derivative. So that will be 1/3. And then the negative of the y partial derivative. And that's going to be 1/2. And then 1 here. Okay, so this is going to be Rx cross Ry here. The curl, the function that we're integrating here, has x's in it. We don't have to do any substitution because we'd be replacing x with x, so that checks out. So what's going to be our integrand? The curl of f dot product with I'll write it out here. So we'll do this dot this. And so the curl is 0, negative 4x and 2x. And the cross product here, giving us the normal vector, will be 1/3, 1/2, and 1. And we end up with 0 minus 4x times 1/2 is negative 2x. Plus 2x times 1 is plus 2x. And what do we notice here? We get 0 as our answer. 0 is our integrand here. So the double integral over the surface S here of the curl of, let me make that look more like the del operator, of this, and the sigma is equal to 0. So by Stokes' theorem, since this is equal to 0, this must also equal 0. And I can assure you this is a much easier way to compute that circulation here than any other method.